Hello everyone, my name is Jesus Rueda Becerril. I'm a postdoctoral fellow at Purdue University at the Department of Physics and Astronomy. Today I'm gonna present part of the work that I've done during my postdoctoral stay at Purdue University. First of all, I would like to thank the organizing committee for giving me the opportunity today. So, the structure of my talk will consist mainly on 4 parts. First, I'm going to give a brief introduction to blazars. Then I will describe the model that we have implemented to our research today. Then I will give you some results, and I will end with some conclusions. But before that, I would like to introduce you the members of this project. Amanda Harrison, my student, and our PI, Dimitrios Giannios. This project was supported by NASA Fermi Cycle 12th Guest Investigator Program, and this work is on the final stage for a publication, so please stay tuned. And for those interested in the numerics of this job, I encourage you to go and have a look to these references. So let's start with the AGNs. Active galactic nuclei are galaxies with their core brighter than the galaxy itself. The standard model of AGNs states that a supermassive black hole is living at the core of the galaxy. This supermassive black hole is surrounded by an accretion disk, by a dust torus, and gas clouds characterized by their emission line features are also surrounding this object. These two are separated by their spectral feature, as I just mentioned, and the innermost is known as the broadline region and the outermost as the narrowline region. The AGNs may or may not have a jet in them, and this separates the two of them into radio quiet and radio loud. We are going to focus today on radio loud AGNs, specifically blazars. Blazars are a subclass of radio loud AGNs with a relativistic jet propagating close to the line of sight of the observer. Show a multi-wavelength double bump structure in their spectral energy distribution. The first bump is accounted for by synchrotron emission, and in a leptonic model, the second bump is accounted for by inverse Compton process. The blazars are classified into two main objects. The observational features that separate these two are mainly that the BLAC show a hard spectra in the gamma rays, while the FSRQs show a soft spectra. The BLAC, they are extreme TeV emitters, while FSRQs do not reach so high frequencies, but they are actually gamma ray louder. The synchrotron peak of the BLAC objects may be observed as high as X-rays, while the FSRQs, their synchrotron peak relies mainly below 10 to the 14 hertz, which is around in the infrared. The BLAC objects, they have an apparent speed close to 1, which means that they are not so extremely relativistic, and they have a low powerful jet. These BL-like objects are thought to be FR1 equivalent, these Fanner of Rayleigh radio galaxies. On the other hand, FSRQs, they do have extreme apparent speed, showing also in the radio that their jets are extremely powerful, just like FR2 radio galaxies. BL-like objects, they usually do not show signs of broad emission lines, while FSRQs have their core obscured by gas with broad emission lines. That on the observational side. On the theoretical side, we know that MHD theory has shown that that relativistic jets are magnetically dominated at their base. They have a bulk acceleration that takes place at the expense of its magnetization, meaning that as the jet accelerates, the magnetization drops, just as we see in the plots here on the right hand side. We can see that the bulk clearance factor, the magnetization, drops, while the bulk clearance factor grows as the jet accelerates far from the core or from the central engine. But something that the theory tells us is that the baryon loading, meaning that the total energy flux per unit resonance energy flux, is constant along the magnetic field lines, which is reduced to this expression for cold plasma. Back to these plots on the right, we can see that the baryon loading here as dashed lines for these different kinds of jets. For further details, I would suggest you to go to Komisarov et al. 2007. We can see that the bulk clearance factor grows as the jet goes farther from the core and reaches the termination bulk clearance factor. But the baryon loading stays constant. So this is something that we are going to keep in mind. So simulations have shown that instabilities may develop along AGN jets because these jets propagate as far as several kiloparsecs or even reach the megaparsec scales. These are long distances that it's highly probable that instabilities may develop in reality. And particularly kink stabilities may actually develop along the jet. Kink stabilities are perfect triggers for the formation of current sheets in the jet, and these in turn are perfect triggers for relativistic magnetic reconnection. Relativistic reconnection is a process that has shown to be perfect dissipator of magnetic energy into non-thermal particles, meaning that this process accelerates electrons into power law distribution, where the magnetization determines the power law index of this accelerated particle. From all these observational, theoretical, and computational results regarding AGNs, we came with a simple model for the emission region of blazars. But before that, we are going to introduce some parameters important in our study. For instance, the radiative efficiency, which is the fraction of the accreted power of the disk that turns into radiation. Also, we define the Eddington accretion rate, which is nothing but the mass accretion rate corresponding to a given Eddington luminosity and radiative efficiency. So with these two, we can calculate the Eddington mass accretion rate, where the Eddington luminosity is given by this expression. So the jet, regarding the jet, we define the jet production efficiency in this form, and the Poynting flux luminosity in this form. For the broadline region, we characterize radiation coming from the disk and producing a radiation field with energy density given by this expression. We are going to set the emission region of the blazar to be at this a certain distance from the core, and this will characterize the radius of the emission region. And in this region, the electrons that are going to be accelerated will have a luminosity in this form. So with all this setup, we take the Eddington ratio defined in this form. So with this parameter, we get to this expression of the jet luminosity as a function of m dot. And according to radio observations, these have shown that there seems to be a correlation between the bulk clearance factor and the jet luminosity. So from these observational results, we are going to propose these ansatz in which m dot is going to be proportional to a power law function of the bulk clearance factor. So in this model, we are going to take in the emission region, the electrons that are going to be injected to the system, and we are going to evolve them. Their evolution is going to be given by the kinetic equation here, and this is going to be solved numerically. The injected distribution of electrons is going to be a power law. The energy losses are going to be of the synchrotron and radiative kind, and the radiation calculated for this system is going to be synchrotron self-absorption, of course, and synchrotron self-Compton and external inverse Compton emission. All of them computed numerically for every snapshot of the electrons distribution calculated here. So, moving forward, we obtained in our results that the cases with baryon loading greater than 100 and low magnetization would give values of bulk clearance factor above observations given by radio, which would correspond to this region here. Also, we noticed that a baryon loading, a very low baryon loading, would give a bulk clearance factor extremely low, which has not been observed so far. So we disregarded those cases. Also, we noted that BLAC, we noted by our simulations, our first simulations, some pathological or non-Blazer-like features for the cases here, here, and here. So those cases have been disregarded in our study. So in this plot, we have that BLAC objects will fall in this region, while FSRQs will fall in this region. Also, super Eddington luminosities may fall in this region, but these are not going to be treated in this study. So after we performed our simulations with this parameterization and considering these sets of baryon loading and magnetization with their corresponding electron power law index, we get the following results. In this plot, we show the spectral energy distributions for the already mentioned, for the baryon loading here, and different magnetizations. We can see that as we have a larger baryon loading, moving from this direction to this direction, we get brighter BLAC objects and also FSRQ-like objects to be louder in the gamma rays. We can see also that with a higher baryon loading, meaning that these two cases, we recover more or less the features or the structure of the Blazer sequence obtained by Fossati et al. In 1998. So we went further with our simulations, and we contrasted our results with observational data, namely the data reported by Ghisalini et al. In 2011. For instance, on the left we have the spectral index in the gamma rays compared as a function of the gamma ray luminosity. We can see that FSRQ-like objects, meaning the low magnetization objects, fall within the FSRQ region, and the BLAC-like simulations fall in the BLAC region. Same thing for this plot, in which we compare the luminosity of the broadline region with the luminosity of the gamma ray band, both normalized to the Eddington luminosity. We can see again that FSRQs fall within the observations, and the BLAC-like objects in the BLAC objects observed. So moving forward, we took radio observations to compare the apparent velocity of our simulations with the data obtained by Mojave collaboration in 2019, and we get consistent results, meaning that we get our FSRQ-like objects fall within the FSRQ observations, and again the BLAC, as we can see, they have a very low apparent velocity and very high synchrotron peak. The gray arrow in both plots show the trend of the increasing luminosity, and these are just for guide, for you to guide. So we have low luminosity objects going towards high luminosity objects. On the right hand, or on the right panel, we can see the Compton dominance as a function of the synchrotron peak. These data points were taken from Finke reported in 2013. The Compton dominance is defined as the inverse Compton luminosity, meaning the Compton component of the spectral energy distribution, over the synchrotron component. So we take both luminosities, we take the ratio, and we get the Compton dominance. So as we can see, the FSRQs are Compton louder, meaning that the Compton component is larger than the synchron component, while the BLAC objects is actually of the order or below the synchron component. These dashed lines are a separation between low synchrotron peak BLACs, intermediately peaked BLACs, and highly peaked BLACs. So, as a conclusion, we get that the blazar sequence may be accounted for with a simple model. All jets are launched with a similar energy per baryon, meaning the baryon loading, independently of their power. And blazars are constrained to mildly baryon loading between 60 and 80, maybe. Relativistic reconnection is a process that accelerates non-thermal particles with a steepness controlled by their magnetization, and this power law index will be translated into their spectral index in the high energy frequencies. And as a summary, FSRQs are powerful jets, while BLACs have weaker jets. FSRQs accelerate to high bulk Lorentz factor, but BLACs do not reach very high bulk Lorentz factors. FSRQs have modest to low magnetizations in their emission region, while BLACs actually have very large budget of energy available for accelerating non-thermal particles. And this in contrast with FSRQs that have a very steep particle distribution. FSRQs show a steep emission spectra in the gamma ray band, while BLACs show a harder spectra above GeVs. Thank you very much.